Here are the various techniques that you can use to reduce dynamic power in your design. You can use gate sizing using smaller gates that consume less power, pin swapping, removing buffers, inverters, merging the gates, selecting datapath components, and clock gating. You can also go with advanced strategies like multi-supply voltages, MSV, by running part of the design at a lower voltage and dynamic voltage frequency scaling, DVFS. If you do not need a higher frequency for certain blocks in your design, you can also reduce the frequency. Power shutoff, PSO, technology lets you turn off power for certain modules using this. Power-aware placement based on vectors and low-power clock tree synthesis, LPCTS. We will be discussing these methods in detail in the subsequent chapters. If you are making some decisions at the architectural level, it has a significant impact on the power consumed by the system. For example, the number of pipeline stages can impact the dynamic power consumption of a design later. Also, low-power techniques like multi-supply multi-voltage are to be accounted for at the architectural level even before writing your RTL. The designer needs to model the low-power system by trading power for performance. You can get a significant power saving at the system and architecture level by voltage scaling. Still, it has some side effects, like if you scale the VDD and threshold voltage, sub-threshold conduction becomes a dominant component of power dissipation. The closer the threshold voltage is to zero, the larger the leakage current. Also, lowering threshold voltage and VDD downscaling leads to greater noise sensitivity in the design. Further lowering VDD can cause delays to increase and thus reduce performance. So, an additional trade-off between active power and performance is required.